Think of it like this. The old methods, like the famous Newton's method, are kind of like throwing darts at a dartboard in the dark. Your first throw gets you on the board. Your next gets you a little closer to the bullseye, and the next one even closer. You can get really, really close, but you can never be 100% sure you've hit the dead center. There's always this tiny little bit of error that means you're not perfectly precise. And this is where things get really interesting. Look at the difference here. On the one hand, you've got the traditional way. You get an approximation, something that's nearly right, but there's always that nagging risk of error. All right, today we're going to tackle a problem that for centuries was thought to be literally impossible to solve with perfect accuracy. We're going to see how a completely new way of thinking can take down a mathematical giant. So yeah, let's just dive right in. So, can a math problem be truly impossible to solve? I mean, really no way to get an answer? You know, we think of math as this world of pure logic, where there's always a right answer. But some problems, they're just on another level of complicated. And finding that perfect, exact solution, it's been a dream, well, until now. Okay, so here it is. This is the beast we're talking about today, an 18th degree polynomial. I mean, just look at that thing. It goes on and on. Trying to find the exact value for x that makes this whole thing equal 0? Yeah, for a very, very long time, that was considered an absolute mathematical nightmare. And you know, it's not just that it looks scary. There was some serious math backing up why it was so tough. For hundreds of years, a super famous theorem basically said, hey, once you get past the 4th degree polynomial, good luck finding an exact, neat answer. It was thought to be impossible. So an 18th degree one? Forget about it. That was squarely in the unsolvable pile. So, what did mathematicians do when faced with a monster like this? Did they just give up? Well, not exactly. They compromised. They used a workaround, settling for an answer that was close enough. It's a whole field called approximation. Think of it like this. The old methods, like the famous Newton's method, are kind of like throwing darts at a dartboard in the dark. Your first throw gets you on the board. Your next gets you a little closer to the bullseye, and the next one even closer. You can get really, really close, but you can never be 100% sure you've hit the dead center. There's always this tiny little bit of error that means you're not perfectly precise. And this is where things get really interesting. Look at the difference here. On the one hand, you've got the traditional way. You get an approximation, something that's nearly right, but there's always that nagging risk of error. But on the other hand, something totally new. A method that promises the exact value, guaranteed precision. Perfectly, absolutely right.
So, how is this possible?
Well, this brings us to the hero of today's story, a truly revolutionary theorem from Murad Sultan Azwidi. And I want to be clear here, this isn't just a slightly better way of approximating. No. This is a completely different way of thinking about the problem, a whole new path. What this theorem does is pretty mind-blowing. It lays out a step-by-step process to find the exact roots, the actual, precise answers. No guesswork, no getting closer, none of that. It's a systematic calculation that just sidesteps the old roadblocks that made everyone think this was impossible in the first place. Okay, don't worry, we're not about to dive into pages and pages of dense, complex math. That's not the point. What's so cool is the idea behind it, which is actually super elegant. The best way to think about it is like distilling something. We're going to boil this monster problem down to its purest form. So here's the process. You start with that big, ugly polynomial. Then you apply this special recipe, a recursive formula, to all those numbers in front of the x's, the coefficients. And as you do that, it's like a chemical reaction. It spits out a brand new set of coefficients, and this is the magic part. It distills all that complexity away, leaving behind only what's absolutely essential. And wow, here's what you get at the end. Just look at this. Almost all of the new coefficients are 0. They just canceled out. All that noise, all that complexity from the original equation, poof, it's gone, vanished. Only 2 numbers are left standing. This is the key to the whole thing. So, this is the moment. This is the big reveal. By changing the coefficients, the theorem has fundamentally changed the problem itself. It took that chaotic, unsolvable mess and turned it into something, well, something beautiful and simple. Just to remind you, this is where we started, right? This monster. 18 different terms, All those crazy numbers, a real headache. And after the distillation, the monster becomes this. That's it, just 3 terms. It's gone from 18 terms down to 3. It's clean, it's simple, and most importantly, it's totally solvable.
But wait, it gets even better. The real genius here is that this new simple equation is something mathematicians call a quadratic in disguise. It looks a little weird, but with one clever little trick, you just say, let's pretend y equals x to the 9th power, the whole thing suddenly transforms into a simple quadratic equation. I'm serious. It's the kind of thing you learn how to solve in your first algebra class. How incredible is that?
Okay, so what's the big deal? We solved one really hard math problem. That's cool, for sure, but the implications of this go way beyond just this one equation. Think about it. In the real world, in physics, in engineering, heck, in cryptography, close enough isn't always good enough. Close enough could mean your bridge collapses or your satellite misses its target. What this theorem shows us is the incredible power of just looking at a problem differently. It's about finding that new angle that gives you perfect precision even when everyone else has settled for good enough.
And you know, the creator, Murad Sultan Ezouidi, said it best himself. He said, this is not just numerical approximation. It provides precise, solvable roots for polynomials that would otherwise be deemed unsolvable. That's not just an improvement, that's changing the rules of the game.
And that's really the idea I want to leave you with. This massive breakthrough didn't happen because we got a faster computer. It happened because someone had a new idea. It just makes you wonder, right? How many other unsolvable problems are out there right now, just waiting for someone to come along and find that one brilliant new way of looking at them?